I locked myself out of my phone. Again.
Wait, didn't you just reset that, like, last week?
I did. I totally did. The bank app forced this whole security update and made me set a new 4-digit PIN.
Right.
And I know I changed it, but for the life of me, I cannot remember what I actually changed it to.
Oh, man. So what's the plan? Are you gonna, like, try to brute force it?
Well, I thought about it. But let's look at the reality here. There are 4 digits, right?
Yeah.
Each spot can be anything from 0 through 9. So it's 10 options for the first number, 10 for the second, 10 for the third, and 10 for the fourth.
Mm-hmm.
That is 10,000 possible PINs. And the kicker is, I only get 3 tries before the bank completely locks me out for 24 hours.
You know, it's actually kind of fascinating.
What is? My misery.
No, well, yes, but also that you just intuitively did the entire foundation of today's deep dive right in your head.
I mean, I think all I did was realize I'm completely doomed.
You did a bit more than that, though. Think about what you just calculated. You took this massive category of, all possible 4-digit pins, and instead of sitting down with a piece of paper and listing them out.
Right, like 000000001.
Yeah, you didn't do that. You just inherently knew to multiply. You found the exact size of the sample space without enumerating a single item.
Okay, well, when you put it like that, it does sound a lot more impressive than just forgetting my password.
It is impressive, and it's exactly the mission of our material today. We're looking at Chapter 2 of an introductory probability course.
Specifically, the lecture slides on counting techniques, right?
Right. Because if we connect this to the bigger picture for everyone listening, we have this beautifully simple formula from the last deep dive.
The probability of an event is just the number of favorable outcomes divided by the total number of equally likely outcomes.
Exactly. Favorable over total. It's elegant.
But it's also, totally useless if your sample space is so massive that you can't actually count it. Like my 10,000 pins. I can't write all those down just to find a denominator for a probability fraction.
And you shouldn't have to. When the sample space gets too large to list manually, we really need specialized math to do the heavy lifting for us. So today is all about mastering 4 distinct counting techniques.
Okay.
And it all builds off that intuition you just used on your phone. The foundation is what we call the multiplication rule.
I think most of you listening probably have an intuitive grasp on this one. If a process runs in stages and each stage has its own set menu of choices, the total number of full outcomes is just the product of all those menu sizes.
Yeah.
So if you flip a coin, that's a menu of 2. You roll a 6-sided die, that's a menu of 6. 2 times 6 is 12 outcomes.
It's incredibly intuitive and a great way to visualize why this works, especially if you're driving while listening to this, so please don't actually try to draw this, is to imagine a branching tree.
Oh yeah, the tree diagrams.
Yeah. You flip a coin, the tree branches into 2 paths, heads and tails. You flip a second coin, and each of those 2 paths branches into 2 more paths. Now you have 4 endpoints.
And then you flip a third coin, and each of those 4 splits again, giving you 8 endpoints. 2 times 2 times 2.
Exactly. Every stage multiplies the leaves on the tree.
But you can see how quickly that tree gets just totally out of control.
Oh, instantly.
Like if you flip that coin 10 times, it's 2 to the 10th power. The tree would have over 1,000 tiny little branches at the end. You are never going to sit down and draw that.
Which is why we skip the drawing and go straight to the multiplication. But let's push this a bit further. In the real world, things are rarely that perfectly uniform.
What do you mean?
Well, the lecture slides introduce a really great complication. What happens to this elegant rule when we start adding constraints?
Oh, like a rule that changes one of the menus halfway through the process.
Yes. Suppose we want to form a new 4-digit number, but we aren't using all the digits like your phone PIN. We are only allowed to use a starting pool of 6 specific numbers. Let's say 0, 1, 2, 5, 6, and 9.
So our default menu size is 6 instead of 10.
Exactly. But here is the constraint. The very first digit of our 4-digit number cannot be 0.
Okay, no 0 up front.
Repeats are allowed, but that first slot cannot take a 0. Does this completely break the multiplication rule?
Well, no, let's walk through the stages. We have 4 slots to fill, right? We look at the first slot. Normally, we'd have our full menu of 6 options, but the constraint says no 0.
Right.
So we literally just cross 0 off the menu for that one specific stage. That leaves us with 5 choices for the first slot.
And then for the subsequent slots?
Well, the constraint only applied to the first digit. So for the second slot, 0 is back on the menu. We have all 6 digits available again. And since repeats are allowed, the third slot has 6 choices, and the fourth slot has 6 choices.
Meaning our final calculation is 5 times 6 times 6 times 6.
Which gives us 1,080 possible numbers.
Exactly, 1,080.
I want everyone listening to notice what happened there. Adding a constraint didn't break the whole multiplicative system.
Not at all.
The underlying structure is completely intact. We still just multiply the stages together. The constraint simply reaches in and, adjusts one specific menu in the sequence.
It's just a localized tweak.
Exactly.
That's a crucial takeaway. But this naturally leads us to a much bigger problem. What if the menus are constantly changing? Not because of an arbitrary rule, but because of the nature of the selection itself.
I see where this is going.
We're moving from independent choices, where you can pick the same thing over and over, to arranging a fixed set of distinct items.
You're talking about drawing without replacement, like every choice you make permanently removes an option from the board.
Yes. And this brings us to our second counting technique, which is permutations.
Okay, let's frame this. Imagine we have 5 distinct letters. Let's just say A, B, C, D, and E. We want to take these 5 letters and arrange them to form 5-letter words. But you have to use each letter exactly once.
Okay, so if we use our slots again, we have 5 empty slots. You go to fill the first slot, and you have all 5 letters in your hand.
Right, so a menu of 5 choices.
You drop 1 letter into the first slot, but when you move to the second slot, you don't have 5 choices anymore.
Because that first letter is gone, you only have 4 letters left.
Exactly. Then 3 letters for the third slot, 2 for the fourth. And by the time we get to the final slot, there's literally only 1 letter remaining, so you just drop it in.
And the multiplication rule tells us that's 5 times 4 times 3 times 2 times 1, which comes out to 120 distinct arrangements.
Yeah. And this pattern, the specific counting down product where you exhaust a pool of items, it happens so frequently in probability that mathematicians gave it its own shorthand.
The factorial.
The factorial, written as an n followed by an exclamation point.
Which, I gotta say, always makes it look like the math is just really, really excited. 5 exclamation point.
It does have a certain energy to it, doesn't it? So n factorial just means the product of all positive integers from 1 up to n. 3 factorial is 6. 5 factorial, as we saw, is 120.
And then it gets big fast.
Yeah.
7 factorial jumps all the way up to 5,040.
It really does.
But before we get swept away by all this, I want to challenge one thing here.
Yeah.
Because I know it trips people up when they see it in textbooks. What about 0 factorial?
Ah, the classic 0 factorial.
Yeah, because the slides explicitly state that 0 factorial equals 1. But if the rule is multiplying everything down, shouldn't multiplying by 0 just make the whole thing 0? Why isn't it 0?
That is a very common point of confusion. And, sometimes you'll hear it explained away as just a convenient mathematical convention.
Right, just so that our formulas don't accidentally divide by 0 and break down later on.
Exactly.
Which, to be honest, always felt like a bit of a top-out to me. Like we're just hacking the math to make it work.
Yeah. It does sound like a hack when you phrase it that way, but there's actually a profound conceptual truth to it. Think about what a factorial represents at its core. It is the number of ways you can arrange a set of items.
Right.
So ask yourself, how many ways are there to arrange 0 items?
I mean, you just don't do it.
Exactly. There is exactly one way you do nothing. In set theory, this is the empty set. There is exactly one unique way to have an empty arrangement.
Wow. So 0 factorial equaling 1 isn't just a trick to keep denominators clean. It's conceptually consistent with the reality of what we are counting.
Precisely. It's the one way to manifest nothing.
That actually makes a lot of sense. Now, while we're talking about the reality of these numbers, we have to pause and appreciate the sheer scale we are dealing with here, because factorials grow at a completely terrifying rate.
They do.
We went from 3 factorials being 6 to 7 factorials being over 5,000.
And if you jump to 10 factorial, you are arranging just 10 distinct items, but that produces over 3.6 million unique combinations.
3.6 million. And what about 20 factorial? You might think, 20 items, that fits in a shoebox.
Oh, not quite.
20 factorial is a number larger than the total number of grains of sand on every beach on Earth. It is an explosively huge number.
Which is exactly why we rely on the elegant notation instead of manual calculation.
Yeah, nobody is drawing that tree diagram.
Definitely not. But this brings up another issue. What if we don't want to arrange the entire beach? What if we have a massive pool of items, but we only want to arrange a small subset of them?
Okay, let's go back to our 5 letters. A, B, C, D, and E.
Perfect.
Instead of making a 5-letter word, what if we only want to pull out 3 letters to form a 3-letter word.
Well, we apply the slot logic again. We only have 3 slots this time. First slot, 5 choices. Second slot, 4 choices. Third slot, 3 choices, and then we stop.
So 5 times 4 times 3 gives us 60 possible words.
Right. The multiplication is easy enough.
But how do we express that using our fancy new factorial notation? We can't just write 5 factorial.
No, because 5 factorial includes the times 2 times 1 at the end, which we didn't do. We stopped at 3.
Right. So what's the notation?
This is where we need to introduce the concept of mathematical division, not just as like arithmetic, but as a conceptual filter.
A filter.
Yeah. If we write out the full 5 factorial, 5, 4, 3, 2, 1, but we only want the 5, 4, 3 part, we need a way to filter out the alternate realities we don't care about.
The 2 times 1.
Exactly. So we take our 5 factorial and we divide it by 2 times 1.
Because the 2's and 1's cancel each other out perfectly.
Yes. And what is 2 times 1?
It's just 2 factorial.
So mathematically, it is 5 factorial divided by 2 factorial.
And where did that 2 come from, practically speaking?
Think about the items.
Oh, it represents the unused items. We had 5 total letters minus the 3 we actually used, which leaves 2 unused letters sitting on the table.
Exactly. So it's the factorial of the total pool divided by the factorial of the unused items. This is the official formula for permutations where we take a subset. The slides call it the NPR formula.
So N permute R, where N is your total pool and R is how many you are picking.
Yes. So the formula is N factorial divided by N minus R factorial. And the absolute most critical rule for permutations is that order matters.
Order matters. Let's ground this in a real-world scenario from the sources to make it clear.
Good idea.
A community foundation has 25 scholarship applicants. They have 3 distinct named awards to give out. Let's say a prestigious research grant, a teaching fellowship, and a community service award.
Okay. If we plug that into our NTR logic, we have a pool of 25 people and we are picking 3. Using the multiplication rule, that's 25 choices for the research award, 24 choices left for the teaching award, and 23 choices left for the service award.
And if you skip the basic math, that comes out to 13,800 different ways to hand out these scholarships.
That's a lot of ways. And we can vividly see why order matters in this scenario.
Absolutely. Think about the applicants as real people for a second. Let's say applicant A gets the highly prestigious research grant, and applicant B gets the smaller service award.
Okay.
If we swap their order, if applicant B gets the research grant and applicant A gets the service award, that is a fundamentally different reality.
Yes. Their resumes look entirely different.
Their career trajectories might change. The order in which they are selected fundamentally alters the outcome we are measuring.
It completely changes the reality. But what if the foundation decides to restructure?
Restructure how?
What happens to the math if they decide to scrap the distinct titles and just hand out 3 identical $500 checks?
Well, if the prizes are identical, suddenly the order in which your name is called doesn't mean anything.
Right.
Whether you're the first name called for a $500 check or the third name called, you are still walking away with exactly the same $500.
The outcome is identical. So if we use our NPR formula and we count applicant A than applicant B as a different arrangement from applicant B than applicant A, we are massively overcounting.
Because we're treating things as different when they are actually the exact same reality.
Exactly. So we need a new tool. When order does not matter, we use our third technique, combinations.
Combinations.
And the intuition here is all about collapsing redundancies.
No.
We need a second mathematical filter. We already filtered out the unused items, right?
Mm-hmm.
Now we need to filter out the redundant sorting orders.
You know what this reminds me of? It's like clearing out duplicate files on a hard drive.
Oh, that's a great analogy.
Yeah, you run a system scan, and you find out you have the exact same massive photo saved in 6 different folders under slightly different file names.
Right, the data inside is utterly identical. They're just sorted differently on your computer.
Exactly. So you highlight all 6, and you compress them down into a single master file to avoid wasting space.
That is a brilliant way to conceptualize it. We need to compress the identical files. So the formula for combinations, written as NCR or NChooseR, is almost identical to the permutations formula.
Okay, so the numerator is still n factorial.
Yes.
And the denominator still has that n minus r factorial filter to chop off the unused items.
Exactly. But the denominator gets one extra piece. and r factorial.
Perfect.
You divide by the factorial of the number of items you actually selected. This compresses out all the ways those specific items could be redundantly sorted amongst themselves.
Okay, so back to our students. If we have 5 students, just keeping the numbers small, and we want to choose 3 of them for identical $500 checks, we do 5 choose 3.
Right.
That's 5 factorial divided by our first filter, 2 factorials for the unused students. And then we also divide by our second filter, 3 factorials, to compress all the ways those 3 winning students could be ordered.
And if you run that calculation, it compresses down to just 10. There are only 10 unique, unordered groups of 3 students you can select from a pool of 5.
Wow. Okay, so we've covered independent choices with menus. We've covered ordered lists where every choice removes an option. And we've covered unordered groups where we compress the duplicates.
We have.
But looking at slides 11 and 12, there is one final overarching rule we really need to grapple with.
The master rule. We need to address what happens when the starting pool itself isn't totally distinct.
Oh, like duplicates right out of the gate.
Exactly. What if we are dealing with duplicates from the very beginning? For instance, taking the letters A, B, B, C, and rearranging them into distinct words.
Right. There are 6 letters total. If they were all completely different letters, we'd just use our standard permutation rule, 6 factorial.
Which gives us 720 arrangements.
But they aren't all different. We have 2 A's. If you literally pick up the first A and swap it with the second A...
You haven't created a new word.
No, it looks exactly the same printed on the page. Same goes for the 3 B's. Swapping any of them around changes absolutely nothing.
So our count of 720 is a massive illusion. It is drastically overcounting the true number of unique words.
So we deploy our hard drive compression trick right from the start. We take our total theoretical count, the 6 factorial.
Okay.
Then we divide it by the factorials of the repeating items. We have 2 A's, so we divide by 2 factorials. We have 3 B's, so we also divide by 3 factorials.
We apply the filters. That's 720 divided by the product of 2 factorial and 3 factorial.
Which brings that massive number all the way down to just 60. There are only 60 genuinely distinct words you can make from those specific letters.
Now, if you take a step back and generalize this idea of splitting a massive pool into smaller, specific-sized chunks of identical items, you arrive at the final concept for today, the multinomial coefficient. This is the ultimate boss-level formula for partitioning objects into multiple groups.
How does that look in practice, outside of just letters?
Imagine you have 10 people in a room, and you need to split them into 3 specific teams. Let's say 1 team of 5, 1 team of 3, and 1 team of 2.
Okay, well, the total number of people is 10, so our numerator is 10 factorial.
Yep.
And our group sizes are 5, 3, and 2. So in the denominator, our filters are 5 factorial times 3 factorial times 2 factorial.
And that calculation compresses down to 2,520 unique ways to partition those 10 people.
You know, I'm looking at this formula, and I just realized something.
What do you see?
This isn't just a new rule to memorize. Think about our combinations formula from earlier, NCR.
Okay.
We were taking a pool of people and splitting them into exactly 2 groups. The group that got the scholarship and the group that got rejected. The chosen and the unchosen.
Yes.
The formula had n factorial on top, and on the bottom it had the factorial of the chosen group r factorial and the factorial of the unchosen group n minus r factorial.
Yeah.
It is the exact same structure. Permutations and combinations aren't separate isolated rules. They are literally just smaller, restricted special cases of this one big master multinomial formula.
That is the conceptual breakthrough right there. Yes, they all flow from the exact same mathematical logic.
It's like a unified theory of counting.
It is. Whether you're arranging distinct letters, picking committees, or partitioning teams, you are fundamentally doing the exact same thing. You are taking a total universe of possibilities and using mathematical division to filter out the alternate realities you simply don't care about.
That is deeply, deeply satisfying. We've synthesized 4 major tools today for everyone listening to help you count massive sample spaces without having to write a single list.
It's powerful stuff.
We started with the multiplication rule, just multiplying the menus at each stage. Then we looked at permutations for when you're arranging distinct items, and order fundamentally matters. We moved to combinations, using division to compress redundant outcomes when order doesn't matter. And finally, the multinomial coefficient, the master rule for partitioning groups.
And the reason we spent this entire deep dive building up this toolbox is so that next time we can return to computing actual probability.
Oh, the real fun begins.
Exactly. With counting fully conquered, our next deep dive will tackle the additive rule, the complement rule, and give you your first real taste of continuous probability.
I am entirely ready for it. But before we wrap up today, I want to leave everyone with one final mind-bending thought about the sheer scale of the math we just learned.
Oh, I like this one.
We talked about how fast factorials grow, right? The next time you are sitting around a table playing cards and you thoroughly shuffle a standard deck of 52 cards, I want you to think about these counting rules,
You're arranging 52 distinct items.
which means the number of possible arrangements of that deck is 52 factorial.
Yeah.
That number is roughly an 8 followed by 67 zeros.
It's incomprehensible.
It is so unimaginably huge that the specific sequence of cards you are holding in your hands has, statistically speaking, almost certainly never existed before in the entire history of the universe.
It is a staggering reality. Every single time you shuffle a deck, you are manifesting a completely unique piece of cosmic history.
It really puts things in perspective.
Okay.
Honestly, it makes my 10,000 possible phone pins feel a little less intimidating.
Well, statistically small or not, you still only have 3 tries left, so choose wisely.